With the Large Hadron Collider running out of places to look for clues to a deeper theory of physics, we're going to need a bigger particle accelerator. And we have one, the galaxy. And the particles the galaxy flings at us may have finally revealed particles beyond the standard model. Physics is currently in a weird place. Historically, no matter how crazy our theories got, there were always new ways to test them. Your theory predicts a new particle? Build a particle accelerator big enough to see it. But once your collider spans entire countries, like the Large Hadron Collider in Switzerland, there's only so much larger you can go, at least on the surface of the Earth. The LHC has thoroughly tested the standard model of particle physics. The last component of that model, the Higgs boson, was verified in 2013. But the standard model isn't the end of the story. There must be a more fundamental theory that explains the origin of this rich family of particles. Proposals for such grand unified theories proliferate, unconstrained by even the tiniest hint of new physics from the LHC. One potentially very important ingredient for grand unification theories is supersymmetry. This is one that physics had really hoped to nail down with the Large Hadron Collider. SUSY is a proposed extension to the standard model designed to fix certain issues with the theory. The most serious issue being that the standard model can't explain the minuscule weakness of gravity compared to the other three forces. This is the hierarchy problem. SUSY provides a very natural explanation for the discrepancy by introducing a new symmetry between the fermions which comprise matter and the bosons which communicate the fundamental forces. As well as fixing the hierarchy problem, this connection between fermions and bosons is in general a step towards unifying the particles of the standard model. It's a key feature in some grand unified theories, as well as modern string theory, leveling it up to superstring theory. Supersymmetry predicts that every single standard model particle has a supersymmetric partner particle of the opposite type. The partners of fermions are bosons, and the partners of bosons are fermions. We'll come back to all of this in detail another time, but the one property that's relevant for today's episode is that these supersymmetric particles are all expected to be way more massive than their known partners in the standard model. To solve the hierarchy problem perfectly, those particles would need to have masses at around what we call the electroweak energy. That's the energy at which the electromagnetic and weak nuclear forces merge into the same force. Physicists had hoped that by smashing particles together hard enough in the Large Hadron Collider, there'd be enough energy in those collisions to produce a supersymmetric particle. And in fact, there should have been, at least for the versions of SUSY that most neatly solve the hierarchy problem. But the LHC has seen nothing. This doesn't necessarily kill supersymmetry, it may just be that these new particles are way more massive than expected. If so, they can still help with the hierarchy problem, though not as neatly as we had hoped. To detect more massive supersymmetric particles, you need higher energy particle collisions. So what, build an accelerator the size of the planet? The solar system? Give up and let theorists just tell their stories? Actually, there is a way to probe energies far higher than is possible with the Large Hadron Collider. The universe itself is a pretty good particle accelerator. Supernova explosions, gamma-ray bursts, black hole magnetic fields are all expected to blast high-energy particles like electrons and atomic nuclei into the universe. These are cosmic rays. The highest energy cosmic rays can have energies around 1 billion times that of the LHC. Unfortunately for particle physics experiments, cosmic rays at these energies are extremely rare, so it's not surprising that we haven't seen supersymmetric particles in our cosmic ray observations yet. Or have we? Let's talk about this thing. No, it's not a downed Imperial probe droid, your rebel base is safe. This is ANITA, the Antarctic Impulsive Transient Antenna. It's a cosmic ray experiment of a very special sort. In fact, it's a cosmic ray detector disguised as a neutrino detector, disguised as a radio antenna, disguised as a hot air balloon. Probably I should explain that. When ultra-high energy cosmic rays travel through space, they bump into the photons of the cosmic microwave background. That's the leftover heat glow of the very early universe. Those cosmic rays lose energy to the CMB, which is partly why the most energetic cosmic rays are so rare here on Earth. But in those interactions, cosmic rays can create extremely high energy neutrinos. Neutrinos are almost ghost-like particles that travel through the CMB unimpeded. So detecting the highest energy neutrinos allows us to learn about the cosmic rays that produce them. These neutrinos don't just ignore the CMB, they can pass through solid matter. Lower energy neutrinos can flow right through the Earth as though it isn't there. We detect neutrinos because very, very rarely one will interact with an atomic nucleus and produce a shower of particles. For example, the Ice Cube Observatory is a 1 kilometre cube of the Antarctic glacier laced with photon detectors. It spots neutrinos when they decay into electrons, muons or tau particles, which in turn produce visible light as they streak through the ice. This is Cherenkov radiation, and Ice Cube's photodetectors track these flashes. ANITA works in a similar way, but it's focused on catching the very highest energy neutrinos, the ones that are produced by cosmic ray interactions with the CMB. In order to see those extremely rare neutrinos, ANITA scans not 1 cubic kilometre of ice, but 15 million square kilometres of Antarctic ice sheet. That's where the balloon comes in. ANITA is a cluster of radio antennae that hovers 37 kilometres above Antarctica. If an ultra-high energy neutrino decays in the ice anywhere within 700 kilometres of ANITA, the resulting radio frequency Cherenkov can be seen by ANITA's antennae. ANITA is designed to detect neutrinos that are coming from below, passing through the Earth into the ice sheet. That allows it to sort out neutrino radio flashes from the flashes produced by other cosmic rays coming in from above. In fact, ANITA expects to see its most interesting, most energetic neutrinos coming in at an angle, skimming the arc of the Earth on a shallow trajectory. They should not come from directly below, which would require them to pass through the entire planet. That's because the most energetic neutrinos actually do lose energy passing through the Earth. They aren't expected to make it all the way through without slowing down significantly. So you can imagine that ANITA scientists were a little confused when they spotted two extremely high energy radio bursts that could only have been produced by a high energy particle passing all the way through the middle of the planet. That's several thousand kilometres of rock, magma and iron. Ignoring the ridiculous distance they travelled, these events look like what you'd expect when a particular flavour of neutrino, the tau neutrino, interacts with the ice and transforms into a tau lepton. That's the heavier cousin to the electron. The tau is cool because it's so short-lived. It produces a Cherenkov burst when it's created, and then a second burst when it decays into a shower of secondary particles. But seeing these very high energy tau events from directly below doesn't make sense. Based on our understanding of the normal background rate of high energy neutrinos, it's estimated that there's around a 1 in 3 trillion chance that 2 tau neutrinos could have been seen in the amount of time ANITA has been looking. Physicists are having trouble accounting for the event with any known standard model particle. Which brings us back to supersymmetry. Astrophysicists Derek Fox, Stein Sigurdsson and team point out that there's a version of supersymmetry that predicts exactly the right particle to do this job. It's the supersymmetric partner of the tau lepton, the tau particle. Yeah, you put an S in front to get the SUSY particle. Selectron, squark, stau. Supersymmetry is super easy. Here's the scenario. A stau particle was produced on the opposite side of the planet by an incoming ultra-high energy neutrino plowing into the Earth. The stau is theoretically capable of zipping straight through the Earth before decaying into a regular tau lepton on the other side. This then causes a high energy radio flash coming from directly below. That's quite a story, but it fits the observations pretty well. There are, of course, other possibilities. It could be a so-called sterile neutrino. Now, we've talked about that before. This particle is also not in the standard model, but has nothing to do with supersymmetry. Hints of its existence have been found in the Fermilab particle accelerator experiments. It may also be that there were some gigantic bursts of regular neutrinos at the time of the observed events. Hit the Earth with enough high-energy neutrinos, for example from a supernova explosion, and at least some of the ultra-high-energy ones could make it through. In fact, one of the two events may have been associated with a distant supernova that was observed around the same time and location. The probability of a chance association with a supernova is around 3%, so it's unlikely, but it does happen. On the other hand, the supernova in question wasn't nearly bright enough to make even one Earth-penetrating ultra-high-energy neutrino likely. And remember, there were two events at different times. The other event wasn't associated with any supernova or gamma-ray burst. The final possibility is just that we're missing something. Perhaps our understanding of neutrino propagation through the Earth is flawed. Or perhaps penguins use cell phones now? This is going to require more observation and confirmation. The first step would be to look at the other big neutrino observatories. IceCube is really the only one that could have potentially spotted similar events. Actually, given the amount of time IceCube has been in operation, it probably should have. Fox and team looked back into the IceCube archive and actually did find some possible high-energy tau lepton events that may have come from directly below. The data is a little ambiguous. They may have been boring old muon neutrinos that can easily pass through the planet, but you can bet people will be paying a lot more attention to these sorts of events from now on. So, have we gone beyond the standard model and proved supersymmetry? Hell no. What we have is a tantalizing hint. Given the painful absence of new particles from the Large Hadron Collider, any hint of something new is bound to get physicists excited. ANITA will keep flying. IceCube will start carefully scrutinizing its data, and if these mysterious events from below keep arriving, you can be sure that physicists will find an ingenious way to confirm their nature. Perhaps we'll verify the existence of the star, and with it confirm the supersymmetric nature of space-time. Before we get to comments, I just want to let you know about 2 Cents, the PBS digital series about personal finance. Financial experts Philip Olson and Julia Lorenz Olson guide you through the complex world of personal finance from the kitchen table to the New York Stock Exchange. You'll get practical knowledge about how to spend, save and earn, and insight into how your brain is hardwired to react to economic problems. If you have any money and might like to have some more, check the link in the description below to subscribe to 2 Cents. Last week we talked about why string theory is so compelling to so many physicists. Now before I get to specific comments, let me address a common objection. Many of you have some interestingly passionate hate for string theory on the grounds that it's so far proved unfalsifiable. Some of you say that means it's not science. Now, I'm not sure I agree with you. String theory may be wrong, but it's not testable due to the limits of the current facilities. Does that mean it's not science? Well, the universe has no obligation to operate in a way that is currently testable by any particular size particle accelerator, nor does it have any obligation to be simple enough to be deduced by even the smartest primates in one generation, or in 100. The thing that makes string theory less sciencey is that its modern version, M theory, is not particularly well defined. But again, that doesn't mean it's wrong. Wolfgang Pauli's "not even wrong" might be a better description. String theory is not precise enough yet to be confirmed wrong, which means it might be right or not. Eddie Galtek asks why you can't get meaningful energy from the Casimir effect. Well, it's the same reason you can't get continuous energy for a ball falling off a roof. You get the kinetic energy once, but then you have to expend at least as much energy raising the ball back to the top of the roof. Same with the Casimir effect. The Casimir plates pull together, giving you a very tiny amount of energy, but to get more energy you have to pull them apart again, which takes just as much energy as you got when they fell together. Dom C asks a good one. To quote, "I thought one of the fundamental properties of the strings was that the maths only works if they are one-dimensional. So, how can you get world sheets?" Yes, it is a pain keeping the number of dimensions straight in string theory. While invariance only works for the 2D world sheet, which has one dimension of space and one of time. This is the shape traced out by a string moving through time. A 2D world sheet has to be traced by a 1D physical object. So yeah, the math of string theory only works for 1D objects because these trace 2D worldsheets. Some of you recalled a recent episode in which we talked about a study of gravitational waves that appears to refute the idea of extra dimensions. Good memory. Actually, this study was specifically evidence against the idea of extra extended dimensions. One explanation for the unusual weakness of the gravitational force is that there's an extra spatial dimension that has the same scale as the familiar 3. So a 4D space in which we live on an embedded 3D manifold called a brane. Gravity then leaks into the extra fourth dimension, causing it to weaken. But this has no bearing on the compactified extra dimensions of string theory. Those dimensions are tiny in extent, and they're coiled on themselves, so there's nowhere for gravity to escape into. It may have implications for the single extra extended spatial dimension of M theory, but I need to research that more. Olivier Westerheide asks if we can make an update video about Oumuamua given the new findings. Well, yes actually. In fact, we're just about to shoot it after these comment responses. To prove it, I won't even change this shirt. And to end on a funny, Dash to the Max points out that string theory is literally like playing a sad song on the world's smallest violin. This is so poetic. If it proves wrong in the end, at least we have the perfect instrument for a requiem to string theory. Thanks to the Great Courses Plus for supporting PBS Digital Studios. Some see string theory as the one great hope for a theory of everything that will unify quantum mechanics and gravity, and so unify all of physics into one great, glorious theory of everything. Others see string theory as a catastrophic dead end, one that has consumed a generation of geniuses with nothing to show for it. So why are some of the most brilliant physicists of the past 30 plus years so sure that string theory is right? Why has string theory been the obsession of a generation of theoretical physicists? What exactly is so compelling about tiny vibrating strings? In our last string theory episode, I talked about what these things really are and covered some history. In short, the strings of string theory are literal strands and loops that vibrate with standing waves. Simply by changing the vibrational mode, you get different particles, analogous to how different vibrational modes on guitar strings give different notes. And, by the way, these strings exist in 6 compact spatial dimensions on top of the familiar 3. In this episode, I'm going to tell you why string theory is right. At least why so many of those geniuses think it is. Maybe I can summarize. It's pretty. Or at least it started out that way. Its mathematics seem to come together so neatly towards a unified description of all forces and particles, and most importantly, that unification includes gravity. I want to try to give you a glimpse into this mathematical elegance. I also want to give you a teaser on why string theory is actually wrong. Don't worry, that topic will get its own whole episode. The greatest criticism of string theory is that it's never made a testable prediction. The space of possible versions of string theory is so vast that nothing can be calculated with certainty. So string theory can neither be verified nor ruled out. It's unfalsifiable. But string theorists might disagree. They might say, maybe half jokingly, that string theory does make one great prediction. It predicts the existence of gravity. Which is stupid, of course. Everyone knows that Isaac Newton discovered gravity when he fell out of an apple tree. Or something like that. There was definitely an apple tree involved. But the fact is, when you start to work out the math of string theory, gravity appears like magic. You don't need to try to fit gravity into string theory. In fact, it will be difficult to remove it. And the quantum gravity of string theory is immune to the main difficulty in uniting general relativity with quantum mechanics. It doesn't give you tiny black holes when you try to describe gravity on smaller scales. We did talk about this and other problems with developing a quantum theory of gravity in a recent episode, But before we get to the nuts and bolts of how string theory predicts gravity, it's worth taking a moment to see how stringy gravity avoids the problem of black holes. Let's actually start with the regular old point particles of the Standard Model. When a point particle is moving through space and time, it traces a line. On a space-time diagram, time versus one dimension of space, this is called its world line. In quantum theories of gravity, the gravitational force is communicated by the graviton particle. When the graviton acts on another particle, it exerts its effect at an intersection in their world lines over some distance. But in very strong gravitational interactions, that intersection itself becomes more and more point-like. The energy density at that point becomes infinite. More technically, you start to get runaway self-interactions, infinite feedback effects between the graviton and its own field. If you even try to describe very strong gravitational interactions, you get nonsense black holes in the math. Okay, let's switch to string theory, where particles are not points, they're loops or open-ended strands. The graviton in particular is a loop. When strings move on a space-time diagram, they trace out sheets or columns. In fact, you can think of a string not as a 1D surface, but as a 2D sheet called a world sheet. Now, let's look at the interaction of two strings. The vertex is no longer point-like, it can't be point-like. Even the most energetic interactions are smeared out over the string, so you avoid the danger of black hole creating infinities. Okay, put a pin in these world sheets, we're going to need them later. They illustrate why quantum gravity isn't hopelessly broken in string theory, and that's a huge point in favour of string theory. But these world sheets will also help us see why string theory predicts gravity in the first place. And this is the second point in string theory's favour. See, it turns out that tiny vibrating quantum strings automatically reproduce the theory of general relativity, and in the same mechanism seem to promise to reproduce all of quantum theory too. This is part of the elegance I spoke of earlier. This stuff appears a little too naturally in the math of string theory to be a coincidence. Or so a string theorist might tell you. For some reason, vibrating strings are bizarrely well suited to quantization. By quantization, I mean taking a classical large-scale description of something, like a ball flying through the air or a vibrating rubber band, and turning it into a quantum description. To do this, you basically take the classical equations of motion and follow a standard recipe to turn them into wave equations with various quantum weirdness added in, like the uncertainty relation between certain variables. I say basically, this is a tricky process, and it only works if your equations of motion are especially friendly. Schrödinger's equation is the first and easiest example. It quantizes the equations of motion of slow-moving point-like particles. A while ago, we talked about how Paul Dirac developed a wave equation for the electron that took into account Einstein's special theory of relativity. It was a mathematical mess until Dirac added some nonsense terms to the electron wave function that caused a lot of the mess to cancel out. Those nonsense terms turned out to correspond to antimatter. The resulting Dirac equation is incredibly elegant, and in the pursuit of that elegance, Dirac predicted the existence of antimatter. This is a powerful example of how following mathematical prettiness can bring us closer to the truth. Quantizing the motion of strings also starts out ugly, but there are also some math tricks to make it work. A big part of it is making use of symmetries. If the physics of a system doesn't care about how you define particular coordinates or quantities, we say that that parameter is a symmetry of the system, or that the system is invariant to transformations in that parameter. Finding symmetries can massively reduce the complexity of the math. A really important type of symmetry in quantum mechanics is gauge symmetry. It's when you can redefine some variable in different ways everywhere in space and still get the same physics. I want to remind you of one particularly crazy result of gauge symmetries. It's a reminder because we covered it, but it's so relevant that it's worth the review. So, we expect the phase of the quantum wave function to be a gauge symmetry of any quantum theory. That means you should be able to shift the location of the peaks and valleys in different ways at different points in space without screwing up physics. And guess what? In the raw Schrödinger equation, you can't. It breaks various laws of physics. But it turns out that you can add a very special corrective term to the Schrödinger equation that fixes these phase differences, preserving local phase invariance. That term looks like what you would get if you added the electromagnetic field to the Schrödinger equation. So, in a way, electromagnetism was discovered in its quantum form by studying the symmetries of quantum mechanics. It turns out that exploring a very different symmetry of string theory both makes it possible to quantize the theory and gives us a very different field, the gravitational field. So, like I was saying, when we try to quantize string theory, of course it's a huge mess. Applying the usual old symmetries got physicists some of the way, but to succeed, they needed an extra weird type of symmetry. That symmetry is Weil symmetry, or Weil invariance. This is a weird one. It says that changing the scale of space itself shouldn't affect the physics of strings. Hermann Weil actually came up with this symmetry right after Einstein proposed his general theory of relativity. He tried to use it to unify general relativity with electromagnetism. Fun story. Weil invented the name gauge symmetry to describe this scale invariance, inspired by the gauge of railroad tracks, which measures the separation of the tracks. Anyway, Weil symmetry doesn't work. Turns out that in 4D spacetime it does matter whether you change the scale of space and the separation of its tracks. But it turns out that there's a very particular geometric situation that does have Weil invariance. That's on the two-dimensional world sheet of a quantum string. Remember that? Mysteriously, the 2D sheet traced out in spacetime by a vibrating 1D string has this symmetry that lets us redefine the scale on its surface however we like. That means we can easily smooth out that surface mathematically and write a nice simple quantum wave equation from the equations of motion. But only for 1D strings making a 2D world sheet, not for any other dimensional object. This is part of what makes strings so compelling. They're quantizable in a way that other structures aren't. But there's a cost to using this symmetry. Just as local phase invariance required us to add the electromagnetic field to the Schrödinger equation, adding Weil invariance means we need to add a new field. That field looks like a 2D gravity on the world sheet. It's a projection of the 3D gravitational field. So, with our quantized equations of motion in hand, you can predict the quantum oscillations of our string. These are particles, and the first mode looks like the graviton, a quantum particle in the aforementioned gravitational field. If you use string theory to write down the gravitational field in what we call the low energy limit, which just means not in places like the center of a black hole, then it looks just like the gravitational field in Einstein's theory. Okay, a caveat. You can only get the right particles, including the graviton and the photon, out of string theory for a very specific number of spatial dimensions. 9, to be precise. In fact, if string theory makes any predictions, it's the existence of exactly this number of extra dimensions. And this is where string theory starts to look less attractive. Our universe has 3 spatial dimensions. String theorists hypothesize that the extra dimensions are coiled on themselves so they can't be seen. But that seems like a hell of an extra thing to add in order to make your theory work. There's also no experimental evidence of the existence of these dimensions. And that's just the first of many problems of string theory. But like I said, we're going to need a whole episode for that. Physicists were led to string theory by the elegance of the math, and the fact that it appeared, at least in the beginning, to converge on the right answers. That convergence is also seen in the union of different string theories by M-theory, and in the discovery of ADS-CFT correspondence, again for future episodes. But can such an elegant and rich mathematical structure really have nothing to do with reality? There's plenty of historical precedent for mathematical beauty leading to truth, but there's no fundamental principle that says it has to. Perhaps we're now overly distracted by the elegance of string theory. Philosophical points to consider as we continue to follow the mathematical beauty, hopefully towards an increasingly true representation of space-time. Thanks to the Great Courses Plus for supporting PBS Digital Studios. The Great Courses Plus is a digital learning service that allows you to learn about a range of topics from educators and professors from around the world. You can go to thegreatcoursesplus.com/spacetime to get access to a library of different video lectures about science, math, history, literature, or even how to cook, play chess, or become a photographer. New subjects, lectures, and professors are added every month. For more information, visit thegreatcoursesplus.com/spacetime. Last week we talked about one of the most misunderstood concepts in quantum mechanics, the idea of virtual particles and their tenuous connection to reality. You guys asked pretty much every question that I avoided. Yuri Nation asks about the photons that mediate the magnetic field or the contact force between two bodies. Aren't they virtual? Well, they are, but they don't exist. These fundamental forces are mediated by fluctuations in the quantum fields of the relevant forces. Those fluctuations can be approximated as the sum of many virtual particles. The particles themselves are just convenient mathematical building blocks to describe a messy disturbance in the field. Eddie Mitch asks whether virtual particles are required to explain the Casimir force. So, the Casimir effect is sometimes explained as resulting from the exclusion of virtual particles between two very closely separated conducting plates, which results in the plates being drawn together. So, if the Casimir effect really is due to a change in zero-point energy, and there are those who say it isn't, but if it is, then it's still misleading to attribute it to virtual particles. More accurately, the conducting plates create a horizon in what would otherwise be a perfect infinite vacuum. In fact, you create two horizons between the plates and one horizon on the outside. Those horizons perturb the vacuum, which can lead to the creation of very real particles, as in Hawking radiation. But in the Casimir effect, the double horizon between the plates restricts what real particles can be produced there, whereas there's less restriction on the outside of the plates with their single horizon. That leads to a net pressure pushing the plates together. David Ratliff asks, if a quantum tree falls in a vacuum and nobody's around to measure it, does it still have energy? Well, believe it or not, it's a serious question as to whether the universe has counterfactual definiteness. Whether or not we can make a meaningful statement about the state of the universe without conducting an experiment. To address this seriously, I want you to imagine this Gedanken experiment. You have a box containing confined poison connected to a radioactive isotope that could either decay or not, releasing the poison. You put a mine in the box. Quantum mechanics can't tell us whether anyone cares. Thank you to 23andMe for supporting PBS Digital Studios. You may have heard the usual pop-sci description of string theory. There are these tiny vibrating strings, and that's where all the forces, particles, including gravity and the entire universe come from. This raises more questions than it answers. Like, why strings? What are they made of? And what's all this nonsense of extra dimensions? In physics, we like to reduce our description of the mechanics of reality down to the simplest possible form. We expect the most fundamental machinery to have the fewest possible moving parts, or free parameters. This is why the standard model of particle physics is considered incomplete. Its equations predict many things with stunning accuracy, but they first require us to tune many mathematical knobs and dials. We need to use physical measurement to fix 19 free parameters like the masses of particles. And then there's gravity, which doesn't fit into the standard model at all. So surely there exists a deeper set of cogs and wheels a theory that brings all observable phenomena into the same mechanical framework. That would be a theory of everything, and this is the great hope of string theory. In the following episodes, we're going to explore the gory details of string theory, but today it's String Theory 101. Where did this crazy idea come from? I mean, why tiny vibrating strings versus literally any other tiny vibrating anything? What exactly are the strings of string theory? First, let's do a quick primer on the origins of string theory. The idea started in the 60s with efforts to understand the behavior of hadrons, collections of quarks bound by the gluons of the strong nuclear force. That includes protons and neutrons as well as mesons, which are a combination of a quark and an antiquark. Peculiarities in the interactions between pairs of mesons, as well as an odd relationship between their angular momenta and masses, suggested that the quarks in mesons are connected by, you guessed it, strings. In this case, the strings are stretched out tubes of strong nuclear force, vibrating elastic bands made of gluons. A lot of work went into figuring out a quantum theory for the strong interaction based on the physics of strings. The theory had some success, but kind of got stuck and was ultimately replaced by quantum chromodynamics. One of the reasons this strong force version of string theory got stuck is that it predicted the existence of unexpected and unwanted vibrational modes in the gluon field of these strings. What's a vibrational mode in a quantum field? It's a particle, and one of those modes appeared to be a massless spin 2 particle. But the only hypothetical massless spin 2 particle is the graviton, the conjectured quantum particle of the gravitational field. If the gravitational field is made of quantum particles, which it might be, we really don't know, but if it is, then the quanta of gravity should have an uncanny resemblance to the type of particle produced by this little investigation into hadronic strings. Except that there's no way anything like the graviton should appear in that sort of string. This realization came in the early 70s. A bold new proposal emerged. Forget mesons. What if the math of this theory could be used in a theory of quantum gravity? In fact, what if all force-carrying particles result from oscillations in tiny strings? All we needed was to make the strings a bit smaller, like 20 orders of magnitude smaller, shrinking from the size of a proton to the Planck scale, roughly the scale of the difference between the Milky Way galaxy and your living room. Oh, and we needed to add 22 dimensions to the familiar 4. No biggie. This was so-called bosonic string theory. If it worked, it would have been a candidate for a grand unified theory, combining all known forces. But why stop there? If wiggly strings can explain force-carrying bosons, why not also the fermions that comprise matter? Through the 70s and 80s, several proposals introduced the idea of supersymmetry to bring fermions and bosons into the same theoretical framework. The resulting superstring theory sought to become an all-encompassing mechanism to explain the underlying workings of our entire reality, a theory of everything. As an added bonus, this ambition also shaved off a bunch of dimensions. Only 10 were needed once fermions were added. Then, in 1995, Ed Witten brought the many forms of superstring theory together into the single framework of M-theory, all for the low price of adding only one more spatial dimension for an 11-dimensional theory. Okay, enough with the history lesson. Let's talk strings. So, wiggly strings could explain the whole universe. That's a hell of a claim. To understand quantum strings, first we need to look at regular strings. They're cooler than you think. The key is that strings can carry waves. And if the string has ends or is tied in a loop, then a wave will end up overlapping with itself. In that case, you get a standing wave. Roughly speaking, when these travelling waves overlap each other, they can either stack up or cancel out. Constructive or destructive interference. Constructive interference only happens if the wavelength of the wave fits a neat number of times along the length of the string. Then the phases of the overlapping wave match in the right way, and that wavelength/frequency of the wave is enhanced. All other frequencies tend to die out. The result is that for a given string, only certain frequencies corresponding to certain energies are possible. These resonant frequencies depend on the length of the string, also its tension, which defines wave velocity and so relates frequency to wavelength. For example, this leads to the specific frequencies of vibration on a guitar string. But this sort of behaviour, where only specific discrete energy modes are allowed, sounds very quantum-like. String theorists weren't the first to notice this. Niels Bohr came up with the first quantum model for electron orbits by thinking of them as ring-like standing waves around the hydrogen atom. But quantum strings are much more ambitious than boring electron orbits. The hope is that tweaked just right, those discrete vibrational modes can be made to match the properties of known particles. Particle mass just comes from the length of the string and its tension. Tension is, after all, just energy per unit length. String length defines mass, but also defines which complex vibrational modes are possible. And those modes in turn define particle properties, like electric charge and spin. So, this is the great promise of string theory. By defining a single parameter, string tension, or equivalently string length scale, all of the possible particles should be automatically defined. Compare that one parameter to the 19 free parameters of the standard model. It sure sounds closer to a fundamental theory. Okay, recap. We have these Planck-scale, one-dimensional structures that can be in loops or extended. They have vibrational modes that define particle properties. By the way, those vibrations, the standing waves, they're not some abstract internal wave. The strings are real physical strands and the waves are wiggles in actual space. But physical strands of what? Common answers include pure mass energy, fundamental irreducible existence, topological irregularities in the fabric of reality, or the most common answer, it's a meaningless question. They are fundamental, so not made of anything. Or in other words, a material known as shut up and calculate-onia. Most string theorists are more interested in what strings do, not what they're made of. So what do? Well, vibrate, obviously. They can hold energy, they can stretch, they can also merge and split apart. These last properties are important because it gives a mechanism for the particles of string theory to interact and to decay into other particles. This picture of strings coming together, joining and splitting apart is a huge strength of the theory. It solves one of the main problems with quantizing gravity. Maybe you remember from our episode on quantum gravity. If you try to describe gravitational interactions on the smaller scales, the energies required to interact on that scale produce black holes. There's no way to even think about the shape of the gravitational field on the Planck scale. That doesn't produce a hopeless conflict. String theory fixes this because the graviton is a loop, not a point particle. Its interactions are smeared around that string, handily avoiding the explosion of mathematical infinities you get below the Planck length. All this stuff sounds great, and, by the way, doesn't work for any other geometrical structure other than a 1D string. So vibrating guitar strings, yes. Drum skins, no. Unfortunately, it's not going to be this easy. Yeah, the strings themselves are 1D, but to even start to produce the properties of known particles, they need to vibrate in more than just the 3 dimensions of space. In fact, the theory only works in precisely 9 spatial dimensions, plus 1 for time, plus 1 for M theory, which we'll come back to. In short, without exactly this number of dimensions, you don't get gravitons or any other massless particle. We'll look into why in future episodes. But this is awkward, to say the least. It's a theory that works in a universe that is clearly not our own, with its measly 3 dimensions of space. But this sort of thing doesn't deter string theorists. There's a way to add extra spatial dimensions that is still consistent with our perceived 3D universe. To get our heads around this, imagine we lived in a 2D flatland universe. We only perceive the giant X and Y directions. But what if flatland isn't truly flat? What if the Z direction has a tiny, tiny width? This is a Pac-Man dimension. Travel the tiny width of this dimension and you'll find yourself back where you started. Very tiny objects, like quantum strings, could explore that extra dimension and, importantly, oscillate in it. But we giant lumbering flatlanders would have no clue it existed. Okay, now scale this up. 3 large dimensions of space and 6 tiny Pac-Man dimensions that only strings experience. Voila! String theory is saved. Modern M-theory proposes an additional large spatial dimension. Our universe of 3D space and 1D time is like flatland on this 5D object called a 5-brane. M-theory unites different string theories because it demonstrates some philosophically fascinating dualities between different ways of thinking about the dimensions. Ultimately, it also leads to the ultimate duality that is the holographic principle. Patience, grasshoppers, we will get there. The exact behavior of strings depends on the shape of their compact dimensions. In fact, the single free parameter in string theory becomes the configuration of the extra dimensions. Find the right location in this string landscape, and you perfectly describe the universe. The only issue is that there are an estimated 10 to the power of 500 possible choices and almost no way to figure out which one is ours. Right now, string theory appears to be at an impasse. It has produced no confirmed predictions. Some would say it's made no testable predictions. Tuning that string landscape to match our universe is daunting and perhaps impossible. Yet, despite this impasse, its promise and its elegance has convinced many that it must be right, or at least the right path. In coming episodes, we'll look deeper into both the successes, the failures, and the profound weirdnesses of string theory. And you can decide for yourself whether you accept the fundamental stringy nature of space-time. Thanks to 23andMe for supporting PBS Digital Studios and Spacetime. 23andMe is a personal genetic company created to help people understand what their DNA says about them. The month of October is Family History Month, which is a great time to explore and learn more about your own family and ancestry. A discovery that can lead to new connections with others. You can learn more by going to 23andme.com/spacetime. Last week we talked about the fundamental computational limits of our universe, and incidentally, what it would take to compute a universe simulation on the event horizon of a black hole. Let's see what you had to say. Roman R asks whether computation at an event horizon would experience massive time dilation relative to an outside observer. So, how do we see the results of the computation? Yeah, that's an issue. Really, you can't read off the results of an event horizon computation until practically ever. I mentioned in the video that you'd read off the results in Hawking radiation, which would take until long after the last star in the universe has died to even give you a small fraction of that readout. The slow readout by Hawking radiation is equivalent to the time dilation issue. You know what? These black hole computers suck. Let's not build one. A few of you pointed out that a black hole computer couldn't store the information about other black holes. And you're right, this was one of the assumptions we made in the calculation. Our supermassive black hole computer is only large enough to contain all information in radiation and matter, but most of the information in the universe is in black holes. Or more accurately, most entropy or hidden information is in black holes. So our black hole computer can't contain the information hidden in all black holes. It can't even contain the information from black holes larger than itself. Yuval Nehemiah went back to an old video that quotes me saying to Neil deGrasse Tyson, "To simulate the universe, you need a computer the size of the universe." In direct contradiction with everything I've said recently about the Bekenstein bound. As hard as it is to believe that I have ever said anything wrong before, I'm afraid Yuval has caught me out. You can build a universe simulator smaller than the universe. That said, the universe simulator that you'd build inside this universe has limits. It couldn't simulate a universe so perfectly that the simulated universe could also contain an equally good universe simulator. There's no infinite set of nested simulators. Like I said, our black hole computer is only simulating particles, not black holes. It's like the simple logical gate arrays that people build inside Minecraft. emulators are never as efficient as the original hardware. Sen Gill tells us, "This was the most boringest video I've ever seen." I have to say, I'm kind of flattered. Have you been on YouTube? Even PBS Digital Studios has spectacular contenders. What about that one where Joe Hansen does nothing but lick a lollipop for over 17 minutes? Or Vanessa Hill's literal "the most boring video ever"? That one's actually quite interesting. Between them, general relativity and quantum mechanics seem to describe all of observable reality, and yet they can't be simultaneously true. They must be united in a deeply undiscovered theory. After a century of work by the greatest minds in all of physics, why does this union still elude us? The first few decades of the 20th century was a time of miracles for physics. First, Einstein's relativity utterly changed the way we look at space, motion, and then, quantum revolution overturned the world. General relativity and quantum mechanics are used to explain nearly every fundamental phenomenon observed. Unexpected phenomena have since been proven. And yet these two theories are fundamental ways. The century since that golden age of physics, we've been trying to reconcile the two with success. But today on the Space Talk, I'm going to begin our discussion of the great quest for this union, the quest for a theory of gravity and for a theory of relativity. This is a big topic in this episode. What exactly are the conflicts between general relativity, or GR, and quantum mechanics? I'll save the solution for future episodes. Let's start with this. General relativity, GR, is Einstein's great theory of gravity. In it, the presence of mass and energy warp the fabric of space and time, and the motion of objects is thereby altered. This results in the effect we perceive as gravity. General relativity incorporates the earlier special relativity, which describes how our perceptions of space and time also depend on motion. Unlike the earlier ideas of Isaac Newton, in which space and time are treated as separate and universal, special and general relativity blend them together into a combined, mutable space-time. Relativity describes the universe of the massive, intimate experts about the subatomic world. It describes particles as waves of infinite possibility, whose observed properties are intrinsically uncertain. Our experience of the universe appears to be plucked from this landscape of possibilities in strange but mathematically predictable ways. That math started with the Schrödinger equation, which tracks these probability waves through space and time. The Schrödinger equation treats space and time as separate in the old-fashioned Newtonian way. So clearly there's a problem. We've already talked about how Paul Dirac fixed part of the problem with a relativistic wave equation for the electron. Nowadays, modern quantum field theories fully incorporate the melting of space and time predicted by special relativity. Yet they still don't directly incorporate the warping of space and time with general relativity. This causes issues. Some mildly fixable, others starting with the mild, we have the black hole information paradox. We've gone on about that at length. The black holes, pure general relativity, swallow information in a way that can move it completely from the universe, especially when those black holes evaporate via Hawking radiation. That's a big conflict with quantum theory right there, which tells us that quantum information should never be destroyed. But that same Hawking radiation offers part of the solution to the information paradox. Following the work of Hawking, Jacob Bekenstein, and Gerard and and others, it has become clear that information stored by black holes can be radiated back out into the universe. In a sense, both the source and the solution to the information paradox came from the discovery of Hawking radiation. Hawking actually derived the latter by finding a way to unite general relativity and quantum field theory. that union was approximate and incomplete. Really, it was just and you can check out the previous episode for the gory details. In fact, it's very possible to shoehorn the curved geometry of general relativity into the way quantum field theory deals with space and time. But that approach completely fails when you have strong gravitational effects on the smaller scales of space and time, like the central singularity of the black hole or at the instant of the Big Bang. For that, you need a true quantum theory of gravity. But even thinking about the structure of curved space on smaller scales leads to craziness and catastrophic conflicts. I want to talk about these in two ways. First, very conceptually, then a bit more technically. Let's start by thinking about what it means to define a location in a gravitational field with perfect precision. Or in other words, what it means to talk about very, very tiny chunks in the fabric of space. In order to measure a location in space, say the location of a particle, you need to interact with it. You would typically do that by bouncing a photon or other particle off the object. The more precisely you want to measure position, the higher the energy of that interaction. That's why we use electron microscopes or X-rays or even gamma rays to take images of extremely small things. So let's say we shoot a particle with a beam from a particle accelerator to measure its location with extreme precision. The Heisenberg uncertainty principle tells us the minimum energy of our beam for precision. It turns out that to measure a position to an accuracy better than a Planck length, around 10 to the power of 35 the amount of energy into the space. It's all with an event horizon of length and diameter. Try to measure more precisely and you need more energy. That means you make an even larger black hole. So general relativity plus Heisenberg say a smaller some viewers will remember the uncertainty principle talks about the trade-off between position and momentum. That large momentum also means large energy. The uncertainty principle also defines the precision trade-off between time and energy. So this same argument can be used to suggest a fragmentation of time. Try to measure any time period shorter than 10 to the power of negative 43 seconds, the Planck time, and boom, black hole. For those of you who already watched our episode on the Heisenberg uncertainty principle, here's another way to think about this. We know that for a particle to have a highly defined location, its position wave function needs to be constructed from a wide range of momentum wave functions that include extremely high frequencies or extremely high momentum. The more certain its position, the less certain its momentum, and so large momentum is possible. So position can be defined to within a Planck length, and then momentum becomes extremely uncertain and includes the possibility of ridiculously high values. That means ridiculously high kinetic energies. Particles whose positions are defined to within a Planck length can spontaneously become black holes. Of course, those black holes don't really happen. Rather, they're an absurdity that tells us that something is missing in our description of either quantum theory or general relativity, or both, at the smaller scales. Let's look at the real conflict. Standard quantum theories treat the fabric of spacetime as the underlying arena on which all the weird quantum stuff happens. Given that sensible underlying structure, it's relatively routine to apply quantum principles or quantize most of the forces of nature. For example, classical electromagnetism becomes quantum electrodynamics when you quantize the electron field and the electromagnetic field. But in the resulting math, the new quantum fields still lie on top of a smooth continuous grid of space and time. So what if you want to quantize gravity? The gravitational field doesn't lie on top of space-time, it is space-time. To quantize gravity, you have to quantize space-time itself. That leaves no clean coordinate system on which to ground your theory. This sounds annoying, in fact it's a disaster. It leads to several problems, but I'll focus on the one that wrongly predicts these crazy fluctuations on the Planck scale. In general relativity, the presence of mass or energy warps the gravitational field. There can be no exceptions. Any energy must cause space-time curvature. If not, you could build perpetual motion machines, for example, using the Casimir effect. In quantum gravity, gravity itself becomes an excitation in our quantized spacetime. the energy of those excitations should themselves precipitate more space-time curvature, represented as further excitations. In other words, gravity should produce more gravity and momentum. This type of self-interaction or self-energy is seen in other quantum field theories, and is already in there. For example, in quantum dynamics, the electron has a self-interaction due to its electric charge messing with the surrounding electromagnetic field. In QED, the mass is fixed with something called perturbation theory. It's a scheme to calculate a complex interaction, like the buzzing electromagnetic field around an electron, with a series of corrections to a simple, well-understood interaction, which might be the electron with a electromagnetic field. We talk about this more in our episode on G-factor. So, perturbation theory is applied throughout quantum field theories of the Standard Model, and it works, because 1. These corrections are small, and 2. Even in the case where the corrections appear large or even infinite, they can be constrained. They can be brought back to reality by actual physical measurements of a few simple numbers in a process called renormalization. For example, measurement of the mass and charge of an electron renormalizes quantum electrodynamics to allow incredibly precise calculation of the electron's self-energy. None of this works when you try to quantize general relativity. When you have strong gravitational effects on the quantum scale, the self-energy corrections blow up to infinity. But unlike other quantum field theories, there are no simple measurements you can do to renormalize those corrections. In fact, you would need infinite measurements to do so. We say that a quantized spacetime of general relativity is non-renormalizable. The non-renormalizability of quantized general relativity is connected to the idea that precisely localized particles produce black holes. Space and time simply cannot behave in the familiar way below the Planck scale. And so the simplest approach to quantizing gravity in space-time must be wrong. Generations of physicists, starting with Einstein himself, spent their lives trying to fix this, to unite quantum mechanics and general relativity. They are still trying. Even though we still lack an accepted resolution, the struggle has not been without progress. There are two main approaches. One is that you search for a way to quantize general relativity in a way that avoids the infinities and non-renormalizability. The leading example of this is root quantum gravity. Or you just assume that GR, and indeed the mutable fabric of spacetime itself, are emergent phenomena from a quantum theory deeper than our currently accepted theories. That's exactly what string theory seeks to do. In upcoming episodes, we'll explore these and other ingenious approaches to crack the greatest problem in modern physics, the quest for a theory of quantum spacetime. Hey everyone, so we haven't done a Patreon shoutout in a while. Why? Because the Patreon crew already hangs out with us on Google Hangouts and on the content selection team, and in general on the Patreon site. Want to hang out with us? Please, we would love to have you, but I digress. Thank you so much, Patreon supporters. You make all of this much easier for us. And today, a special huge thank you to Justin Murray, who's continuing to praise our level. Justin, and a special thanks for sending me a box of Planck scale black holes. With our modern understanding of Hawking radiation and light, they will evaporate catastrophically long before they do. Let us know if you think it'll really help us constrain this. Okay, so on to the responses. Today we're covering both the black hole entropy enigma and the challenge question episode. How much information does the universe contain? A few of you asked why it is that the surface area of a black hole on the horizon must always increase, and the mass and radius can actually decrease. Now let's talk about the latter. When two black holes merge, a lot of energy is pulled into gravitational waves. There's only one place for that energy to come from, the mass of the black holes. As a result, the mass of the final merged black hole is smaller than the sum of the masses of the two originals. The horizon radius is proportional to mass, and so the radius of the final black hole is smaller than the sum of the originals. Note that the final black hole is massively larger than either of the original black holes taken separately. Then there's the Penrose process. it's possible to extract energy from a rotating black hole by throwing in objects on near-miss trajectories. The rotating black hole drags space around with it, and the incoming object absorbs some of that rotational energy, traveling out at a higher speed. The loss of rotational energy by the black hole also means a loss of mass. But rotating black holes are slightly squished. As they lose spin and angular momentum, they become more spherical. In that process, the event horizon only changes shape. It doesn't change the surface. To best take points out, it's important to emphasize that you're talking about the observable universe, not the entire universe. And I totally agree. For those of you who have doubts, the challenge question is the size of the storage device needed to store all of the information in the observable universe. I said observable near the start of the episode, but I dropped that observable part a couple of times later on. That's my bad. Voodoo Dog points out that the vacuum isn't really empty, what with all the virtual particles popping into and out of existence, so what about real information? Well, actually, those don't really contain information because they aren't real in the sense that we think of normal particles. The phantom virtual particles represent both the absence of particles and every possibility of particles, but in both cases, there's no specific defined state to keep track of. No real quantum states means no information, except perhaps whatever information you need to track important properties like vacuum energy. YouTube account asks whether the universe has ever been in a state of too much information in too little space, particularly during the Big Bang. That is a really great question. In fact, it's a great extra credit question. I'll make sure one of our winners is selected from those who answer this question in their submission. Clue: you'll need to go beyond the formula for the Bekenstein bound in terms of event horizon surface area. The more fundamental formula is in terms of radius and contained energy. Have at it. Rubber-Gnome is skeptical about 't Hooft's solution to the black hole information paradox and cautions that we don't neglect other interesting ideas like complementarity, the membrane paradigm, fuzzballs, and holography. Well, to be fair, we did mention complementarity in the information paradox episode, and 't Hooft's ideas are the gateway to holography. We'll get to fuzzballs, or better known as the black hole triple hypothesis. A century of Earth's radio transmissions has now washed over thousands of other star systems, carrying with it some of our greatest broadcast masterpieces, as well as our worst reality TV. What are the chances that alien civilizations have detected and even decoded these signals? We are a young technological civilization. An advanced alien race monitoring our planet, even from the nearest neighbouring star, would have seen nothing. Radio quietness, until only around a century ago. Then, beginning with the faint sporadic buzz of the first experiments with wireless transmission, the radio brightness of this small planet would have bloomed into a continuous planet-wide cacophony of TV and radio broadcasts, satellite relays and radar pulses. This bubble of chatter is, as I speak, spreading out into the galaxy at the speed of lights, the unmistakable signature of an emerging technological power. The outer edge of this bubble is now over 100 light years away, and it carries with it the first transatlantic radio transmission of Marconi himself. That edge may be hopelessly diffused, but it's followed closely by the much brighter 80 light year shell, on which rides the footage of the 1936 Berlin Olympics, episodes of The Lone Ranger, and Orson Welles' ill-fated radio adaptation of War of the Worlds. That shell has several thousand star systems. Based on Kepler Space Telescope observations, that also means thousands of potentially habitable planets. Lots of chances for hypothetical civilizations to have learned of our existence. So the question is, who could have seen us? What manner of civilization would be powerful enough to sense this bubble? Technically, actually decoded the signal patterns. If aliens arrive at our doorstep tomorrow, they have been alerted to our presence by Nikola Tesla's first experiments, broadcast footage of the moon landing, the Phantom Menace? To answer the question of who can see us, it's helpful to first ask, who could we see? After all, humanity remains the one example of a technological civilization, for now. Our best astronomers have been engaged in the search for extraterrestrial intelligence, SETI, in earnest since the 60s, when Frank Drake first peeked at the stars Tau Ceti and Epsilon Eridani. Drake peered into the so-called water hole, a narrow frequency range in the radio spectrum between a pair of H and OH emission spikes, which itself is within the broader window from 1 to 10 gigahertz. There, the natural universe is especially quiet. Surely this is the window where aliens would choose to broadcast their messages welcoming us into the galactic community. And of course, Drake saw nothing. Decades of SETI programs followed, utilising several of the world's great radio telescopes, like Arecibo in Puerto Rico and the Parkes Radio Telescope in Australia. These searches often focused on the water hole, or the surrounding quiet frequency window. But with the exception of some one-off oddities, the search was not successful. The 1977 WOW signal is the most compelling, a narrow frequency radio blast detected in the water hole that still has no broadly accepted natural explanation. But no one ever saw it again. Apparently no one is trying particularly hard to get our attention, and it's important to understand that these searches could only have been successful if there were deliberate, powerful beacons emitted by an alien civilization. The radio leakage produced by their own internal broadcasts would be much harder to detect. Our best targeted search so far, the SETI Institute's Project Phoenix, scanned 800 stars within 200 light years. At that range, it could have picked up a gigawatt beacon beamed directly at us. But it would only have picked up leakage from a civilization's internal broadcasts from within a couple of light years, if those broadcasts were the same strength as our own. In that range, there is exactly one star, ours. An alien civilization at exactly our current tech level would never have seen our TV bubble. We have sent out more powerful beacons, like the stream of 10,000 tweets and celebrity videos that Arecibo blasted in the direction of the WOW signal. But that's a long shot, and perhaps for the best. I'm not sure we want our first contact to be a typical slice of the Twitterverse. One of the reasons it's hard to spot unintentional radio leakage is that a distant civilization's radio bubble is likely to overlap in frequency with our own transmissions. This is another advantage for searching for alien signals in and around the water hole. At around 1500 megahertz, it's in the ultra-high frequency UHF band. Most TV broadcasts are at the tens to hundreds of megahertz of the merely very high frequency VHF band. VHF works better for over-air broadcasts because it carries further and is less blocked by buildings and such. So we often search the UHF to avoid the thick soup of our own VHF chatter. But surely aliens are working with the same physics that we are. Perhaps we miss each other because we can't easily peer through our own local VHF soups. But there is a way to peer straight through our own radio noise as though it wasn't there. The answer is interferometry. Two radio telescopes separated by a large enough distance can filter out local transmissions. A signal that appears in one but not the other must be an earthly transmission. Now that's not the main purpose of interferometry. That is to increase the spatial resolution of your observations. You get the resolution of a telescope as large as the separation of the component telescopes. Also super useful. Interferometry has been around for a while, but we're only now building an interferometer facility with the sensitivity to potentially see an alien TV bubble to many light years. And that is large enough to filter out local noise. It's the Square Kilometre Array, or SKA. The SKA is actually many telescopes. Arrays of thousands of radio dishes will be built in Africa, and hundreds of thousands of antennae installed in Australia. When connected up, It'll effectively form a giant radio telescope with over a square kilometre surface area. But as an interferometer, it has the resolution of a telescope thousands of kilometres across. Its sensitivity and pinpoint resolving power will be vastly greater than any telescope of any type that we have ever built. The SKA is not being built to search for aliens. One of its primary purposes would be to catch the radio emission from hydrogen gas in the extremely early universe. That emission, produced at 21 centimetres wavelength, or 1420 megahertz frequency, is by definition one of the boundaries of the water hole. But if such radio waves travel to us from the earliest of times, then they become stretched out as they travel through an expanding universe. That redshifted early hydrogen emission is now found slap in the middle of the noisy lower frequency part of our own TV broadcast spectrum. To spot these radio photons, we need a truly gigantic interferometer, both at extreme sensitivity and to eliminate our own radio buzz. That's the SKA. Such a machine also just happens to be perfect for spotting alien television bubbles. According to the calculations of Harvard University's Avi Loeb and Matthias Zaldariaga, the SKA should be sensitive enough to spot our own TV bubble from 100 or more light years away. So will we soon be picking up extraterrestrial sitcoms? Not quite. Loeb and Zaldariaga's numbers assume pointing SKA at a target star system for an entire month and adding up all of the radio emission over that time. For an artificial radio source, that would look like emission over a narrow frequency range that doesn't correspond to any natural process. These emission spikes may also shift back and forth in frequency due to Doppler shift as the distant, technologically advanced planet orbits its star. So that's enough to identify a technological source, but not to actually decode the signal. An alien civilization with their own SKA certainly couldn't watch Earth TV. To do that, they would need to achieve SKA's 1 month sensitivity in a tiny fraction of a second. That means compensating for the difference in exposure or integration time with sheer size of the telescope. Let's figure it out. What would be needed to, say, tune in to the first season of the original Star Trek series? That signal is now 50 light years away. Assume a bit rate of 10 million per second for a miserable 30 frames per second at 200 by 200 resolution and only 8-bit color. Forget audio, which is a shame because the original series dialogue is awesome. The aliens would need a radio telescope trillions of times the SKA's surface area, and equivalent to a dish around 3 times the radius of the moon's orbit. That's conceivable for a Type 2 civilization, but it's exceedingly unlikely to be We may even be a little optimistic in thinking that the SKA will detect alien TV. As the SETI Institute's John Billingham, along with James Bedford, point out, that 1 month integration time requires a very consistent narrow frequency signal, which may not be consistent with typical broadcasts. But remember, humanity is young as a radio noisy civilization. Simple probability says that any other civilization is likely to be ahead of us on the curve. It's not hard to imagine them building a much larger SKA without going full Type 2. Our SKA will cost a few $1 billion by the time it's done in 2030. That's a significant investment, but only a tiny fraction of the global GDP. For a slightly more advanced civilization, that's several Moore's Law doublings ahead of us in various technologies, and accounting for moderate GDP growth over a century or two, a super SKA with several hundred square kilometres of collecting area would constitute the same degree of investment as our own 1 square kilometre array. In that case, Earth's TV bubble would be spotted within hours or even minutes of aliens pointing the facility to our solar system, even if they weren't looking for us. Surely any advanced civilization is curious about its own origins. That redshifted 21 centimetre hydrogen emission really is one of the most important keys to understanding the very early universe. It's pretty natural to want to scan the heavens at exactly the frequencies where we Earthlings are the noisiest. If there's a slightly more technologically advanced civilization within our radio bubble, they've probably seen us. However, our steady broadcasts have only washed over a few hundred solar-type star systems, and only a few thousand stars total. Technological civilizations would need to be extremely common throughout our galaxy, and I mean tens of millions of them across the Milky Way, for there to be any chance that there's another one so close to us. But we just don't know. If anyone else inhabits this very local region of the galaxy, then they may have been aware of us for some time now. Any civilization within 40 to 50 light years could send between 60 that will reach us any day. Their fleets of welcome ships will be a little further behind, but no doubt carry only the best wishes for their noisiest neighbours in nearby space-time. Hey everyone, I just wanted to say thanks again to those of you sponsoring us on Patreon. I want to give a very special shout out to Lunar IT Solutions, who are sponsoring us at the Quasar level. Thanks a ton, it really is a huge help. A couple of weeks ago we leapt back into black holes and studied the nature of the event horizon. You guys had some excellent and quite tricky questions. Lucasino asks what we would really see if we followed the monkey directly through the event horizon. Would it appear ahead of us despite previously appearing frozen on the event horizon? Well, sort of, yes. The light from the instant of the monkey's crossing of the event horizon is eternally trapped at that horizon. It's trying to walk upwards on a downward escalator of space-time. But you're travelling down that same escalator, and so you pass this light, and so you see the instant of the monkey's crossing. The escalator speeds up as you descend, and so light that the monkey emitted from below that point is trying to go up, but is actually going downwards. And yet you're travelling downwards faster, so you overtake some of that light, which means you see the monkey ahead of you. Douglas Oak asks a great question that I've heard asked before. If time dilation approaches infinity, do you reach the singularity before the black hole evaporates? Okay, so a distant, immortal observer with a ridiculously good telescope will detect photons from the fallen monkey at all future times. Eventually, those photons will come billions, even trillions of years apart from each other and be hugely redshifted. For an eternal, non-blinking black hole, there is no last photon. But real black holes decay, and so the final burst of Hawking radiation as a black hole evaporates will be accompanied by all of the remaining light emitted by everything that fell into it as it crossed the event horizon. But the infalling stuff isn't saved. Although we never saw the moment of its crossing, that did happen. Its matter became part of the black hole and re-emerges as that Hawking radiation. Grin Reaper of Trolls is curious about taking their warp drive into a black hole. Well, I would encourage it. You can escape a black hole by travelling faster than the speed of light. In principle, you can do that with a warp drive. The probably impossible technology of the warp drive allows you to cause a patch of space to move at really any speed you have the energy to reach. So you could resist the faster than light flow of space within the black hole. The event horizon itself just wouldn't apply within your warp bubble. You know, there's probably a Penrose diagram for this. I'll look into it. Some people complained about my use of the expression escape velocity greater than the speed of light at the beginning of the episode. First, let me note that I gave that statement in a list of popular examples of oversimplifications about black holes. Second, it's not actually an incorrect statement, despite the derision it receives in nerd circles. It's accepted to talk about the escape velocity at the surface of the Earth because we're used to Newtonian approximations there, but it's no less accurate near a black hole. At the event horizon, you need to travel at the speed of light relative to the black hole's stationary frame of reference as recorded by a distant observer. That's the velocity you need to escape. The reason that people poo-poo the expression escape velocity is that it reminds us of a strange coincidence. You happen to get exactly the right size for the event horizon if you use Newtonian gravity to calculate the distance at which the escape velocity reaches the speed of light. The correct way to get this number is by using general relativity to find the point where the flow of space-time reaches the speed of light. But the concept of escape velocity at the event horizon is still as meaningful as it is from the surface of the Earth. It's a useful classical simplification in both cases. Corner Record asks about that thing when you're in a black hole and time becomes space and space becomes time. Well, that's probably a topic for an entire video, so for now I'll just quote what's in it. The inward direction acts like the future direction. So once inside the horizon, avoiding the singularity is like avoiding next Tuesday. This episode is supported by the Great Courses Plus. The idea of Dyson spheres has captured our imaginations. Vast megastructures capable of harvesting the power output of entire stars. The as yet inexplicable Kepler Space Telescope observation of swarms of somethings partially eclipsing a distant star has led to some rampant speculation. Today we ask, are Dyson spheres plausible, and are they inevitable? In 1960, astrophysicist Freeman Dyson proposed that a sufficiently advanced civilization would have such extreme real estate and energy requirements that they might build artificial habitats in the form of vast shells surrounding their parent star. Such Dyson spheres would be possible targets for our search for extraterrestrial intelligence, appearing only as strange points of infrared light, but otherwise black at visible wavelengths. We don't really know how the energy requirements of advanced civilizations evolve. It may be that their most natural progression does not require cosmic levels of consumption. On the other hand, securing access to an entire star's energy output officially elevates a civilization to Type 2 on the Kardashev scale. We're currently Type 0, so obviously it would be nice to unlock the achievement. Let's assume that access to 10 to the power of 26 watts is desirable. Are Dyson spheres the way to go? The plausibility of a solid sphere the size of a planetary orbit is not really in question. They are not plausible. The incredible stresses on a solid structure that size are vastly greater than could be sustained by any known or yet imagined material. Even if a super advanced material with enough strength was discovered, you'd need impossibly large quantities, much more than there is non-hydrogen or helium matter in all of the planets in the solar system. The sphere would not be habitable, having only a tiny gravitational pull at its surface, and that would be towards the sun. And finally, it would be hopelessly unstable. Any small bump would cause one side to fall into the sun. Some of these issues could be dealt with, but in the end it's just not an efficient way to start your galactic empire. So do we ditch Dyson's original idea in our quest to reach Type 2? Not so fast. It's not feasible to build a giant solid sphere, but collecting the entire output of our home star may still be the smart choice. In fact, we can get around all of the issues I just described with a simple adjustment. Instead of building a Dyson sphere, build a Dyson swarm. Individual solar collectors that are only kilometres or less in diameter, and each with its own independent, stable orbit around the sun. Build enough of these, and you can read the entire sun in all directions, absorbing its entire energy output. The crazy thing about the Dyson swarm is that we could probably start building one in the not too distant future. In fact, we could get started on the first collector pretty much right away. The thing that makes it seem a crazy prospect is the sheer scope. We have to disassemble entire planets for the raw materials alone. But believe it or not, there's a plan. It was proposed by Stuart Armstrong, AI expert and futurist. The idea is to cannibalize the planet Mercury. And that's just to begin this war. Mercury is ideal because it has a gigantic solid iron core, comprising over 40% of the planet's mass. Combine that with the abundant oxygen in its crust, and we can make hematite, a naturally occurring, highly reflective iron oxide that's been used for millennia as primitive mirrors. Each of the swarm's collectors would then be a giant polished hematite mirror, perhaps a kilometre across, but as thin as tinfoil. It would reflect light into a small solar power plant that would then beam energy somewhere useful, perhaps with a laser or a maser. The other nice thing about Mercury is that its gravity is low enough that launching mined raw material into space for construction is pretty efficient. Building the first collector would be the slowest. We start with limited mining, space launch, and orbital construction facilities, all of it autonomous. Energy supply is the big limiting factor at the start, so it takes about 10 years to build the first collector. But once it's complete, we can build and manage to use it to power electric vehicles, building new mining and replicators. It's an excellent process. Every collector increases the energy available to build more collectors. Within 7 years, and Mercury is nothing more than a debris cloud. To fully encompass the Sun, we'd probably need to devour Venus, Mars, and a good number of asteroids and outer solar system moons too, assuming we want to leave Earth intact. Well, let's assume that. Sound over the top? It's totally nuts, but it's likely doable. Autonomy in manufacturing, mining, and transportation are all progressing exponentially. Engineers are in the serious planning phases for all sorts of space-based assembly projects, including 3D printing of giant telescope mirrors. Real companies are gearing up to do autonomous asteroid mining, perhaps within a couple of decades. And all of this is without considering nanorobotics. There's no obvious field. Fraction of the sun's energy, or trillions of times the current energy output of the planet. What we then do with that energy is another matter. But is the Dyson swarm really the best path to Type 2 status? Would other civilizations have gone that route, casting very conspicuous shadows on neighboring stars for us to detect? The advantage of using sunlight is that the sun is already making it. However, in terms of power efficiency, it's not all that great. Only 0.71% of the rest mass of the ingoing hydrogen fuel at the sun's core is converted to energy. Also, we need a megastructure to harvest it, with a raw material requirement close to that of all the terrestrial planets in the solar system. Is there a better way? Maybe. What if, instead of converting 0.7% of fuel rest mass into energy, we could achieve 100% efficiency? Antimatter engines do this, but currently it takes more energy to create the antimatter fuel than we get back out. Well, perhaps we can do better there, but there are also other options. For example, black hole engines. Energy can be harvested from a black hole, either from the Hawking radiation, from heat generated from infalling material, or by extracting angular momentum from the black hole's spin. We talked about one example, the Kugelblitz, in our previous episode on possible Starship engines. Socio Space also did a great episode on the Kugelblitz. Tapping the Hawking radiation from an artificial black hole is appealing because, once formed, we could perhaps sustain it from evaporation by feeding it with new matter. This is really a 100% efficient conversion of mass into energy, assuming we can find a way to pump new matter into the proton-sized Kugelblitz against the tide of Hawking radiation. And we only need 1 billion Kugelblitzes to equal the sun's output. That's nothing compared to the hundreds of quadrillion solar collectors in a full Dyson swarm. Added benefits: we get to keep Venus and Mars, and also Kugelblitz and other 100% efficient mass converters are indefinitely scalable. The Dyson sphere/swarm can absorb at most the entire energy output of the Sun. However, there's enough mass in the solar system to run a Type 3 civilization's Kugelblitz swarm for many times the current age of the universe. Of course, the trick is making the black holes in the first place. To make an industry standard 600 million kilogram Kugelblitz, it takes something like 10% of the sun's energy output each second focused into a single atometer at a single instant. But wait, that's the power we get from even a partial Dyson swarm. So there's something to do with the swarm's energy. Burn through Mercury, then use that partial Dyson swarm's energy to build Kugelblitzes in orbit, say, around Jupiter. Type 3, here we come. Maybe this is why we don't see Dyson swarms all through the galaxy. Aliens build partial swarms to provide the energy to build more efficient engines, which would be essentially undetectable. Or they try building their first Kugelblitz and it goes very, very badly. Either way, Fermi paradox solved. Admittedly, the fading that the Kepler Space Telescope observed in Tabby's star is sort of consistent with a partial swarm. I guess it couldn't hurt to point some radio telescopes to look for power leakage from the Kugelblitz swarm. But no, it's never aliens unless every other explanation is exhausted. Now we don't go in for that hokey stuff here on Spacetime. Thanks to the Great Courses Plus for sponsoring this episode. The Great Courses Plus is a service that allows you to learn about a range of topics from Ivy League professors and other educators from around the world. Go to thegreatcoursesplus.com/spacetime and get access to a library of different video lectures about science, math, history, literature, or even how to cook, play chess, or become a photographer. New subjects, lectures, and professors are added every month. I learned a ton about energy production and use from Professor Y Session. With the Great Courses Plus, you can watch as many different lectures as you want, anytime, anywhere, without any tests or exams. Help support the series and start your 1-month trial by clicking the link below or going to thegreatcoursesplus.com/spacetime. Hey guys, quick announcement. We'll be taking a break week next week while I travel, and then coming back the following week with the answer to the Quantum Eraser Lottery Challenge, and some intriguing physics news. Also, I'm planning to head to Austin for South by Southwest in September to do a panel that we're calling We Are All Scientists. It'll be with Joe Hansen from It's Okay to Be Smart and Katie Mack, astrophysicist and cosmic genius. But first, I want to ask you guys to head to the South by Southwest panel picker page, link in the description. Just need to make a quick account and vote for our panel. Please and thank you very much. A couple of weeks ago we talked about the mysterious delayed choice quantum eraser. There was some heated discussion. A few of you pointed out that an important bit of info was omitted from the description. Now, we did this because we wanted to expand on that point through last week's challenge question. Now that we've done that, we can talk a bit more about it. The point is that in order to resolve the photon distributions at the screen, you need to know which detector was triggered by every one of those photons' entangled twins. This is done with coincidence electronics. If we see exactly the right time offset between a hit on the screen and a hit at one of the detectors, that means that those two photons were an entangled pair. After the experiment is done, we can pick out off the screen all of the photons that had twins hitting, say, detector A. Those photons turn out to show no interference pattern. But the photons associated with C or D do have an interference pattern. However, there's no way to figure out which photons correspond to which detectors until the arrival times at the screen are compared to the arrival times at the other detectors, and that information has to be sent at regular, slower than light speeds. In a way, this is even more crazy. Those locations are recorded on the screen, and the interference patterns are embedded in them. Those interference patterns hold the information about future events, but we can't extract that information until those future events have occurred, and we can compare notes between the screen and detectors. We'll go into all of this in more detail in the challenge question answer, and also when we come back to quantum entanglement. On a related note, David Stagg would like to know what the interference screen looks like before you know what the data is at detectors A, B, C, and D. Well, the screen just looks like a blur of photons. See, it's not just that the blur of photons connected to detectors A and B are overlaid with an interference pattern from C and D. No, even C and D produce a blur until you compare coincidence data. As I mentioned in the challenge question, the interference pattern of C has the opposite phase to that of D. Its peaks line up with D's valleys and vice versa. It's like adding a sine and a cosine wave. It adds up to a flat distribution, and it's only when you look at the photons connected to C and D separately that you see the bands. Jose Aturia would like to bring up the topic of the Berenstein Bears. Good one. I actually got that. Are we alone? Recent amazing discoveries have given us more hope than ever that our universe is full of life. So why don't we see it? Why don't we see alien civilizations? We've asked this question before here on Spacetime, and if you haven't seen that episode, you should check it out. But today, we'd like to go deeper because it really does seem like there should be aliens. The Kepler Space Observatory has told us there are a couple of 100 billion nice orderly planets in the Milky Way, and probably billions of them are Earth-sized planets around sun-like stars. Many of them have been around long enough to produce a civilization that could have easily colonized the entire galaxy by now. So why is the Milky Way so un-Star Warsy? This genuine oddity is referred to as the Fermi paradox, and the resolution for it has to be that there's some sort of great filter that either makes intelligent life extremely rare in the first place, or that wipes out essentially all advanced civilizations before they get to the galactic empire stage, whether by nuclear war, environmental catastrophe, accidentally making a black hole that swallows the planet, etc. Personally, I'm not buying it. I just don't think that there's an inevitable great filter still ahead of us. As we saw in a previous episode, we're not so far from building starships ourselves. Surely some civilizations must make it through these growing pains and manage to reach the stars. So, where are they? Well, there's another deeply sad and deeply inspiring possibility. Humanity may be one of the very first interstellar species in the history of the galaxy. But before we get all emo, let's science this right. We know of exactly one instance of intelligent life happening, the case of Earth. And as if it wasn't hard enough to do statistics with a sample size of 1, we also have to deal with a massive selection bias. Of course we're going to observe at least one instance of intelligent life happening, because we are that one instance. In a way, it doesn't matter how improbable sentience is, as long as it happens once, it will be there to observe itself. Here we're touching on the anthropic principle, which states that an observer will always observe a universe that can make observers, or a planet that can. We'll talk about the cosmic implications of this more in another episode, but for now, we need to acknowledge that this selection bias allows that life could be extremely rare, or even unique. Given that, can we even begin to assess the likelihood of life out there? Yeah, we can science anything. So, let's dig into whether we should really expect to see a Solarian empire. Let's take the knowns. Now, Earth certainly required a number of very special conditions to build life, and it's hard to know how essential each of these was, or how frequently these conditions are met through the galaxy. I'm going to avoid the details of the biology here, because we can say a lot just based on how much time it took to get through each step on the path to building technological life. We can crudely summarize the big leaps that led up to intelligent life as 1. Assembly of self-replicating RNA from organic molecules. 2. RNA-based protocells. 3. DNA and the first actual cell. This is the moment of abiogenesis, life from not life. 4. Increasingly complex single cells. 5. The first multicellular organism, so plants, animals, etc. And 6. The first intelligent life form capable of counting to 6 on YouTube. Now the crazy thing, the thing that I find the least intuitive, is that the first 3 steps in that chain combined, the appearance of true cellular life, happen faster than any of those later steps. So fast, in fact, that it seems hard to believe. And in fact, so fast that our galaxy probably should be brimming with at least simple life. Let me explain. See, around 4 billion years ago, pretty much just after the Earth had first cooled down from being a giant hellish magma ball, we think that it totally got pounded by a meteor storm that lasted a couple of 100 million years. This is the late heavy bombardment, and it probably obliterated the surface. We think we know this because we flew to the moon and found evidence of it. Up until recently, the earliest known evidence of life dated to roughly 3.5 billion years ago. Fossilized blue-green algae beds, stromatolites, found in Western Australia. The place was covered in this greenish-purple slime that reeked of rotten eggs. Yeah, the beach was horrible back then. Basically, Earth was once a giant slime ball. And it looks like Earth went from magma ball to slime ball in less than 300 million years. What? That seems crazy fast. But it also suggests that this first step, the genesis of life, is not the great filter. But wait, the abiogenesis thing gets even weirder. See, nature has provided us with the perfect time capsule for studying the very early Earth. Zircons, super hard silica crystals whose formation can be dated precisely by the ratio of decaying uranium versus lead decay product locked inside. And get this, just recently a zircon was found containing the possible signature of life, and dated at 4.1 billion years ago, from before the late heavy bombardment. That little crystal contains what looks like biogenic carbon. That's a fancy way of saying there's too little carbon-13 compared to carbon-12. See, photosynthetic life finds C12 a bit yummier, and so it absorbs more of that than the heavier C13. Pretty much all carbon enters the biosphere from the photosynthesizing bottom of the food chain. Any carbon that's been through living systems will have the same C13 light isotopic ratio that we see in the circle. Now there are other non-biogenic explanations, but this is extremely suggestive that life was abundant on Earth, remarkably soon after it first coalesced from stardust, and that life either survived the late heavy bombardment or formed again after. Or the late heavy bombardment never happened. That's actually a possibility too. But either way, it looks like Earth became a slime ball teeming with life in a crazy short amount of time. How on earth did this happen? Two options. One, given the right conditions, the genesis of life happens like that. And two, it didn't happen. Life proceeded from space. In a vehicle and panspermia. Look, there's no question that lots of rock gets ejected into space after meteor impacts and can move between planets. We found plenty of meteorites originally from Mars. A lot of the ejecta from Earth is going to be swarming in bugs. Could similar bacterial astronauts have once survived an interstellar journey to Earth? Some bacteria are certainly hardy enough to survive launch and landing. This has been tested. If these bacteria were frozen solid, they could plausibly survive a very, very long journey. And you only need 1 out of billions to make it. Maybe the solar wind pushes infested material into interstellar space, so that tens of thousands, even millions of years later, a single bug winds up on a brand new planet and boom, instant slime ball. Questionable. But it would mean that life only needs to evolve once from scratch in any given galaxy. Now this should be very testable. Earth was infested fast, so that means this stuff should be out there. Mars must have been hit when it had water. Did it go slime ball? There should be something like stromatolite fossils on its ancient surface. We haven't seen them yet, but they'd be hard to spot. These cosmic cooties should be findable in space too. So, either fast abiogenesis or panspermia. One of them must be true. However, both suggest that the galaxy should be teeming with slime ball planets filled with life. Now that's exciting. We don't have the telescope to find them yet, but we could soon. These planets will have atmospheres driven by biotic processes. If we could analyse light passing through these atmospheres, we would see signatures of oxygen, ozone, methane, nitrous oxide at concentrations impossible without a biosphere. Properly fund NASA and its terrestrial planet finder, and we could find extraterrestrial life within 20 years. So it's entirely possible that we'll soon discover that the galaxy is filled with life. But this just makes it weirder that the Milky Way isn't swarming with ancient alien civilizations. There is a filter, but it's not the genesis of life. The clue might be that the Earth stayed a slime ball for nearly 3 billion years. The first multicellular organism turned up only 600 to 800 million years ago, and life as we know it quickly exploded after that. Was this a random lucky event that we just had to wait for? No. Multicellular life evolved independently dozens of times. It just took a really long time for those single cells to become complex enough to form large collaborative structures capable of collective reproduction. i.e. plants, animals, a species capable of making the Kerbal Space Program. And speaking of space programs, technological life took a little while longer, but not really so long on the overall scale. Once we had complex life, after the Cambrian explosion, it was only around 500 million years to go from jellyfish to moon landing. Of course, maybe the emergence of intelligence is a random and unlikely event, and this one is the hardest to assess. However, it's worth noting that we do have other species on Earth that seem to be moving down the same big-brain path independently of humans. So what is the Great Filter? Maybe it's just time. If life is common, then of the billions of Earth-like planets in the galaxy, only a tiny fraction needed to have a small head start on us in order to have produced the Federation of Planets and Stargates and stuff by now. So what if humanity started? Of all of the sun-like stars and Earth-like planets that will ever form over the full past and future history of star formation in our universe, Earth is early. It's part of the first 8%, according to recent Hubble Space Telescope-based calculations. We have emerged in the epoch of life, in a universe abundant from the rich resources of past supernova explosions, and after the violence of the starburst and quasar complex. It's strange believability to imagine that we didn't really warrant that telescope. And it is possible that we are a very early outlook, that any other civilizations are so distant as to not be apparent. Is humanity a first-generation intelligence? One of the species we'll watch and maybe die as other intelligent life emerges throughout the galaxy? Well, there's something to learn to us. In the next episode of Space Talk. Last week we talked about Miguel Alcubierre's warp drive. You guys had a lot to say. Let's do it. A lot of you noticed my mistake in saying that Miguel Alcubierre is Spanish rather than Mexican. That was my mistake. We cram a lot of details into each episode of Space Time, and sometimes things like this do slip. So thank you for catching it. Miguel Alcubierre was in fact born in Mexico and in fact educated up to master's level. Eric Villas wonders what it would look like seeing an Alcubierre warp bubble race by from the outside. This is tricky. The bubble would definitely leave some sort of light signature, because light inside the bubble can traverse the walls in any direction besides forwards. And our negative mass matter may also end up on the outside. Because the bubble is superluminal, any light that we see would trail the bubble, just like the sound of a supersonic jet. Ahead of the bubble, you'd see nothing unless it stopped, in which case all the photons and particles that captured on its journey would blast you into oblivion. Now, a few of you took issue with my statement that it's never aliens. And fair enough, it's never aliens until it's aliens. The point of this philosophy is that the alien hypothesis is a bad place to start, because you can explain almost any weird natural phenomenon as having been produced by a super intelligent, extremely high-tech civilization with inscrutable motives. Really, anything. It's a weak hypothesis until you've genuinely ruled out everything else. Or you actually see the mothership and take an unsuspiciously blurry photo. Sir Nate asks if we can please do another challenge episode. Absolutely, we'll do one soon. Thank you to CuriosityStream for supporting PBS Digital Studios. We are currently being visited by a traveller from outside our solar system. This is the first time we've ever seen an asteroid-like object that came to us from interstellar space. Today, on Space Time Journal Club, we'll see what mysteries it can unlock. On October 19th this year, astronomers spotted an unusual object moving rapidly away from the Sun. The discovery was made by PanSTARRS, the Panoramic Survey Telescope and Rapid Response System, a group of telescopes that constantly monitors the sky for moving or variable objects like asteroids or comets. This object was initially thought to be a new comet, but after 34 days of follow-up observations and a bit of orbital mechanics, it became abundantly clear that we were looking at the first object ever observed that came from outside our solar system. The mysterious object has been dubbed 1I, the first object in a brand new International Astronomical Union class, with I standing for interstellar. 1I also scored a more poetic name, Oumuamua, from the Hawaiian meaning a messenger from afar arriving fast. Now, this object was first spotted several weeks ago, but by now we've had time to study it with many of the world's great telescopes. For this Spacetime Journal Club, we'll be discussing what we've learned about Oumuamua since its discovery. Our focus will be on a paper by a Dutch team from Leiden Observatory, Portuguesois et al. 2017, PZ17 for short. This paper, which is still under the process of being peer-reviewed, looks at the possible origins of this strange object. Before we get to its origins, let's look at the object itself. It's pretty weird. It's highly elongated, like a cigar, or the monolith from 2001 Space Odyssey, hundreds of meters long. Its size and shape can't be determined directly from the images, it just appears as a faint dot, even to our most powerful telescopes. However, it varies in brightness with an irregular period, and astronomers realised that this is consistent with an elongated body with a tumbling motion. We've seen such tumblers in our solar system, and it suggests a major collision in the object's past. Oumuamua doesn't have a tail like a comet, so its surface isn't vaporizing in the sun's radiation. That suggests the surface, to at least 1 meter depth, is rocky like an asteroid rather than icy like a comet. Or it could be the flickering exhaust jets of an alien scout ship returning to report a planet ripe for invasion. But no, it's never aliens. The weirdest thing about Oumuamua is its motion. Every previously observed asteroid, indeed every previously observed everything in our solar system, moves in elliptical orbits as governed by Kepler's laws. The eccentricity of the orbit measures how stretched out the ellipse is. Eccentricity 0 is a perfect circle, and eccentricities less than 1 are elliptical orbits, meaning the object is gravitationally bound to the Sun. The Earth, for example, has an eccentricity of 0.0167, giving us a nearly circular orbit, while Halley's Comet has an eccentricity of 0.967. That's an extremely stretched out ellipse. Objects with eccentricities greater than 1 follow unbound hyperbolic paths. They never actually orbit the Sun, rather they're deflected by the Sun's gravity as they pass by. Oumuamua has an eccentricity of 1.2, meaning its hyperbolic